All right, for those of you that don't know what this is here, because we're talking about the SMD UAV solder practice board, this is KiCad. It is an EDA tool, electronic design tool, that application that we use for creating, developing, designing PCBs, circuit boards. What I want to show you here, we got right here, this is your schematic. So this is the logical symbol that you use when you're creating, and by logical I mean pretend, right? The thing that represents the actual item. And then up here, this one that I'm clicking on now, this is the actual circuit board itself. This is where you define the actual shape of the part that's going to go on there, and where the pitch of the pins, how far apart they are from each other, and actually start placing them around the board. So I'll quickly show you a look at both. So I open this up, and this is the schematic. So most of you probably understand and recognize schematic symbols. You might not know what they all mean, but you understand that these are pretend little symbols that are used to define certain types of objects. So for example, this one right here is a resistor. This is the one that I've been using forever, but technically this is the European standard. The United States uses a scribbly one. It's just like a jaggedy line. This here is an LED. This is an NPN transistor. Down here is another resistor. These are just test points. So there's that. Let me move this out of the way, and then I'll show you the circuit board, and you'll recognize this, because this is the board we're working on. Now, you can't quite see it the way it is right now because you're looking at the front copper layer, but if I go to the front silk screen, now you can kind of see the outline that we see on the board that we're working with. I can look at this in three-dimensional view, and that will become a lot more explanatory, you see? So then I could roll it around. So this is nice. So this is a section where you actually define, like in the last video, there is our 100 ohm resistor that we soldered on. I made this pad right here, the footprint they call it, that this is going to span based upon what the data sheet of this resistor said that its length and width was. And then maybe then you give yourself a little extra, this little extra right here, so that we can solder. Again, from the last video, that gives us a little bit of extra pad there to create a nice little fillet. So I'll close that, come back to this. So this is here. I got another view for you here. Now you can see it without all of the rest of the copper layer that's there, and you can see all the individual devices. So you take these, you move them all around, and then by hand, you wire them. Okay, there's a little bit more to it. Obviously, there's more to it, and there's some stuff that makes it a little bit easier. There's a lot of stuff that makes it a bit more complicated, right? It's basically a bit of a puzzle trying to sort this all out. So I will close this. I'm not going to save it. And we'll go back to the schematic, because this is what I want to talk about today. I want to talk about this resistor right here. This is the 5K ohm resistor that we need to solder on. This is where we left off last video. Now, as I said in the previous one, I wrote on the board 5K because that seems kind of okay, kind of middle ground of maybe what it should be. But to do some testing, potentially later down the road, I got a 1K, 3K, 10K, 100K to see how much of a difference it makes. To determine that, I guess I have to tell you what its job is first. So I'm going to try to say this and keep it as much of an overview as possible and try to make it simple but explanatory so you understand what's going on. This NPN transistor right here, think of it like a switch. Let's start with this. That if I were to push this button, say it's a button right here where my cursor is, if I were to push that, then it lets current flow through this device. So we have power coming in up at the top here, stopping right here, you push the button, and then it flows through. Great. Now, the pushing of said button is not done by your finger, it's done by Arduino pin 2 in this case. So I'm going to zoom out for a second and kind of bounce over to here just to show you what I'm talking about. Here is the logical, not the actual size, shape, and size footprint, but this is the logical schematic diagram of the Arduino development board that we have that's going to go onto our board. Right here is Arduino pin 2, and what will happen is we'll write some code in here that says turn on the LED, let's say. Turn it on. And then it'll say turn it off. Turn it on, turn it off, turn it on, turn it off. Great. So we come back over to here. And you see, here's where it comes in. There's going to be a wire that jumps from here to here. This is because it's a solder practice board. Normally it would just be straight connected. And so when that signal happens, it says turn on, then it's going to put a small voltage, 5 volts, on this pin right here of this NPN transistor, which will be the equivalent of pushing the button. And so then it will turn it on. Now, to the specifics of this. This pin, this button, will turn on with a pretty small voltage. It doesn't have to be much. It just has to have a little bit of some current flowing through here to get this to turn it on and let this in from the top. Again, I'm doing my best to dodge some deeper specifics. When we turn on the Arduino pin and that voltage comes over here to this pin, like I said, it turns it on. When we turn it off, when the Arduino says off, what can happen is you can end up with a little bit of electricity on this wire right here. And that small amount of power that's there can cause this pin to stay on. You see what I'm saying? Now, if your switch turns on and then off, and then maybe it waits for 5 seconds, 10 seconds, 20 seconds, then it turns on for a little bit, then it turns off, and it waits again for 10, 20, 30 seconds, maybe this might not actually end up being such a big deal. But if it's turning on faster and it needs to be triggering something else very responsively, that we need that voltage to disappear quite quickly if it builds up. So what this is a resistor going to ground right here. Imagine right now if we just took the resistor out, you have this pathway and you send electricity down it and it goes to this pin. If this went straight to ground, the electricity will shoot down here and shoot straight down here and go right to ground and essentially have maybe no voltage left, no power left to turn this switch on. So we add a bit of a restriction to it. We put a bit of a resistor here. Maybe it's a tiny one, just enough to where it'll let some through. Maybe it'll let a lot through, but it will let some more this way. So do you see what I'm saying here? We're creating a restriction that causes it to want to flow both ways, because if there's no restriction, it's going to just jump straight down to ground. So let's roll with that for a second. We have a small restriction here. We have a lot of current flowing down through here. When you have a lot of current flowing, you have a lot of heat being built up. And with heat, you have energy loss. So that is a big or a small problem, depending upon what it is that you're trying to do. If you're trying to run this system off of a battery and have it last as long as possible, and maybe your competition that's making a device just like yours, if theirs lasts longer than yours, then you might end up not selling many. So it's going to eat up power. So then you increase the size of the restriction, the resistor, and then it lets more flow through here and a little less go through here. Good. So the thing is working. It dissipates the energy that's there to ground, and the thing turns off pretty quickly. Now, if we keep increasing the restriction, pretty soon you're going to end up with a situation where it's almost like not even having this, where you can end up with a bit of built up energy right here that holds this switch on, and very slowly the energy trickles to ground through the resistor. So that's going to make, let's say it's a light, that's going to make your light stay on a little bit longer and then slowly fade out, possibly something like that. So then you decide to start bringing the resistor back down to where your light, your circuit, whatever it is, turns off fairly quickly. You bring it down too much, you have energy losses. You bring it up too much, then you have the light, the thing staying on too long. And so this is the balance that you want to try to do with this device right here. So this is a resistor. It's a resistor just like the one, here's the one that we soldered on previously. This is a current limiting resistor for this LED. This resistor and this resistor down here are the same thing. They're the same construction. They almost look exactly identical, except for the numbers are different. But we call this a current limiting resistor because of its place in the circuit. It's resisting the flow of current, resisting to keep the light from being too bright and damaging itself, and we can increase it a little bit more to maybe, dim it down. This one over here is allowing the electricity, the current, the power. I'm trying to, again, keep things kind of vague. It's trying to give it a place to go to ground. It's trying to take this circuit here and pull it down to ground. Maybe slowly, maybe quickly, depending upon, again, how you size this, okay? So this one right here is called a pull-down resistor. Normally this circuit, let's say, is off, and then when you activate it, it goes up, so now it's 5 volts, and then you want to pull it down. Sometimes the circuit is predominantly on, so it's up at 5 volts, and every so often you turn it off, you turn it off, you turn it off. Well, in that case, you could have the same problem, but in reverse. So you might have this resistor going up, let's say, to hold it at 5 volts, and then you pull it down to ground every so often, and it will snap it right back up to 5 volts. Okay, so we have pull down and pull up resistors. So then that's what I wanted to tell you about the circuit before we get to actually soldering on the one on the board itself. Okay, so same thing as last time. We're just going to go ahead and solder all the 0805 resistors into the 5K spots, but we're going to go ahead for now and use the 3K ohm resistor. That should be sufficient to get us started. It should work just fine. And then maybe later down the road, we or you or whoever, we can decide on if we want to desolder those and try playing around and see what different values do what. So what I do here, by the way, if you caught in the fast motion of the last video, I'll knock out the 3 on one side. I'll just put them over here and flip them all over, and then I'll do the other side. The reason for that, reason I don't dump all of them out, is because if I'm soldering these over here, I can guarantee I'm going to knock these all around over there and lose them somewhere. So I'll set that off to the side. Get my magnifying glasses on, get some goop all over the place. Oh, see, that's how things get lost. Okay, we're good.